So today we're going to be covering chapter 14, which is just going to go over some weather. So like the last couple of weeks, this is going to be a lot of material that you already know, and a lot of things that you probably hear in just day-to-day normal life. I know that the syllabus states that we would also be going over chapter 15, but since we lost a week and everything is so crazy right now, I'm not even going to bother with the solar system. Let's just keep everything in this course Earth-related. So this is going to be the last lecture of the semester. So before we can really get into weather, we need to talk about air masses. So an air mass is just this huge body of air. We might think of air mass being like the wind blowing, but air masses are gigantic. They're going to be thousands of miles across, and they can cover an entire continent in just a single air mass. And these air masses are also incredibly thick. Again, we're talking about miles thick of air. But when we are looking at an air mass, if we just look at any specific altitude, like one layer of that air mass, you're going to see that regardless of where we are, the temperature and the humidity are going to stay the same. So the temperature is not going to get warmer or colder in another area, and it's going to have the exact same amount of water vapor at any part of that layer of that air mass. But again, as we increase our altitude, we're going to see that things are going to decrease in temperature. So this having the same temperature only applies if we're looking at like one specific altitude. Let's say like 500 kilometers above the surface. But when these air masses move, again, the Coriolis effect is constantly moving the air around in our atmosphere. We're going to see that it's going to affect the entire weather system of an entire continent. So all of our weather, whether it's a nice sunny day or if it's just pouring the rain, it's all due to these air masses moving around and interacting. This is just called air mass weather, or just day-to-day life, we call it weather. So when we're looking at these air masses, it's important to know exactly where this air mass is coming from, or its source region. So we talked about wind last week, and hopefully I emphasized it enough, but we always base wind on where it's coming from, not the direction that that wind is moving towards. So with our air masses, we want to know where is that air coming from. And we're going to classify it based on the latitude, where it is around the equator towards the poles, and by how much air pressure, or sorry, how much humidity is going to be in the air. So when we're looking at the latitude, we're going to have three different types of air masses. We're going to have polar and Arctic. These are going to be really cold air masses. And then we also have a tropical air mass. So that's going to be a lot of warm air. But we're also going to see that our air mass, how much humidity is in that air is also going to be really important. So the air masses that form over our continents, they're forming over solid rock. That air is going to be really dry. But if we're looking at air masses that are forming over our oceans, they're going to have a lot more water vapor in them, and it's going to be very humid. So again, the two things when we're trying to identify where these air masses are coming from, the two things that we want to concern ourselves with is the latitude. How hot or how cold is that air? And did it originate over a continent or over an ocean? It's going to tell us how much humidity is in that air, or the amount of water vapor stored inside of it. So there are a lot of different air masses, but we're just going to focus on the five basic ones. So with these, they're either going to be continental and dry, or maritime and have a high humidity. But remember, we also want to know what latitude is it coming from. Basically, is it going to be warm or cold air? So we're going to have our continental polar. It's going to be really cold, dry air. We're also going to have a continental Arctic. This is going to be the driest and the coldest possible air that we can form. We also have a continental tropical, which apparently is not shown on this map. Oh, here it is. With this, it's still going to be dry because it's continental, but because it's tropical air, it's going to be warm air. Then we also have this maritime polar. Now it's forming over the ocean, so it's going to be really humid. But because it's polar, it's going to be cold air. And then finally, maritime tropical. Basically what we have here, just warm, humid air that forms over the oceans. Because it's forming over the oceans, it's just going to have a lot more water vapor or a higher humidity in that air. But we're going to see that the boundaries of these giant air masses are going to be important because it's going to form fronts. You check the weather, they might talk about a cold front or a warm front moving through. So when the boundaries of these air masses are moving, they're going to cause different weather conditions. But once that front, the actual boundary passes through, the air mass is going to just have physically the same type of weather that's going to occur after the front moves through. So the front is the only part where we're going to get like nasty thunderstorms or something. But just like where we saw that warm water rises because it's less dense, we're going to see that warm air also rises and cold air is going to sink. So whenever we have warm and cold air interacting with one another, we're going to see that the warm air is going to be forced upwards by that really cold, dense air. It's going to act like a wedge and just force all of that warm air higher up into the atmosphere. So we're going to have different fronts that form depending on what type of air mass is behind the front. But if we were to look at a weather map, we're always going to see things with like these lines with different colors and different shapes on them. And here the symbols are actually going to be important. If you see red semicircles, this is telling you that a warm front is moving through. So that means that behind the actual front, the boundary of this air mass, we're just going to have really warm air behind it. But because warm air is not dense, it's just going to move upwards. It's going to go over the cooler air beneath it. But we're going to notice that the height of our clouds are going to be really low-lying clouds near the front. And then as we get farther away from the front, those clouds are going to get higher and higher in our atmosphere. And I want you to notice the slope of the boundary between the warm air above and the cold air below. It's a relatively gentle slope. And this causes the warm front to move very slowly. But as we start making warm and cold air interact, they're going to react to one another. So if you've ever been in a place that's like really cold inside and really warm outside, you might notice like condensation will form on windows. We're going to see the same thing happening at the boundary between the warm air above and the cold air below. So these warm fronts are going to bring in precipitation. So almost every time we have a warm front moving through, we're going to have some form of precipitation that follows the front. But we also have cold fronts. And here, this is where our cold air is moving into an area. And again, because cold air is a lot denser and it's going to sink, it's going to follow right along the surface. And it's going to force the warm air that it's touching high up into the atmosphere. So you'll notice here that the boundary between the cool air and the warm air is a lot steeper. So it's twice as steep for these cold fronts than it was for the warm fronts. This is going to allow the cold front to move a lot more quickly than a warm front does. But here, you'll notice that the symbols are going to be blue triangles. And again, the side that these symbols are facing is telling you the direction that front is moving towards. So here we can see blue triangles on the right side, telling us that the cold air is moving towards the right. With our warm fronts, we just saw precipitation. But when our cold fronts move through, because of that really steep gradient, and this air is moving so quickly, we have some really violent and destructive weather that's going to form during these cold fronts. So here we're going to have really intense rain. It's going to pour, but it's going to generally be a very short storm. But once this cold front has moved through, once the boundary has already passed, and we're just in the cold air mass, we're going to see that it's going to be very clear conditions. We're not going to see any more rain, and we're just generally going to be a very cloudless day because all of the air is under high pressure. It's all sinking because it's so cold. But we have two other fronts as well. So with the stationary front, we're going to have an air mass that's not really moving. So it's stationary because it's sitting still. So with these stationary fronts, they can last for a couple days where the weather isn't going to change at all. We're not going to see any kind of precipitation or any extreme weather. That air front is just going to stay exactly where it is. But we also have an occluded front, which is what these images are showing. So with an occluded front, we have a cold air mass that's moving and it's catching up to another cold air mass. Remember that these cold air masses move a lot more quickly than the warm air masses. So if there's warm air stuck between these two cold air masses, it's going to get stuck and it's going to be forced above all of this cold air. It's going to kind of be wedged out. And with these occluded fronts, we have crazy weather that occurs. And it's actually like really complex weather. But again, as we're forcing this warm air up, we're going to start seeing precipitation. So basically, any time that we are interacting, we're forcing cold and warm air to move past each other. We're going to have some form of precipitation. It might just be a small shower in the case of a warm front, or it could be a massive storm in the case of a cold front or an occluded front. So when we are looking at these different types of fronts, I'm just going to focus on warm and cold because they're the most basic. But we're going to see very specific weather associated with these warm fronts. So we're going to see really low and really thick clouds whenever the warm front is getting ready to pass through an area. Again, if we're forcing cold and warm air to move past each other, we're always going to have some form of precipitation. But with a warm front, it's going to be a light precipitation. It's just going to have a brief shower. And then once the actual front or boundary of this air mass moves through, we're just going to have very warm temperatures for the rest of the day. It's not going to rain anymore. It's just going to be a very warm day. We're going to see the exact opposite with cold fronts. Again, these are the ones where we're going to get really extreme storms. So we're going to have those entire blankets of really dark clouds that tells you it's about to rain. But with these cold fronts, we also see extreme weather. We're going to have not only really large storms that's just pouring the rain, but we're also going to see things like hailstorms and tornadoes developing from these cold fronts. But after the front, where the boundary has moved through the area, now we're just dealing with a bunch of cold air. So the skies are going to clear up. It's not even going to be cloudy. And we're going to just be experiencing colder air. It's just going to be a cold day outside. So for, I think the rest of this chapter, we're just going to be focusing on different types of storms. We're going to start off with thunderstorms and then move into tornadoes and hurricanes. So with thunderstorms, we had a great one this morning, but these are actually the most common type of major storm that happens on our planet. So at any given second, there are over 2,000 thunderstorms going on in the world, but they happen more in certain places. So if you look at this map along the top, you'll notice that the red areas, this is where we get the most lightning. And most of this is right around the equator. So here in Florida, we're relatively close to the equator. We're actually the place in the United States that have the most frequent thunderstorms. Generally, about 100 days a year, we're going to have a thunderstorm somewhere in Florida. But with these thunderstorms, we need those cumulonimbus clouds. Remember those clouds of vertical development that are not only in high or low portions of our altitude, it's going to span from very low areas near the surface all the way into very high portions like 6,000 meters above the surface of the planet. And the reason why we need those really tall clouds is because we need these clouds to be producing a really significant amount of rain. We're never going to have a thunderstorm where it's just barely drizzling outside. It's always going to experience very heavy rainfall with some lightning and thunder. But if our thunderstorm gets severe enough, we can also have hail. Those little balls of frozen ice, where the ice is just being pushed up to the top, where it's getting colder inside of that cloud. It's going to freeze another layer of ice before it drops back down to the bottom. And it's just going to keep cycling until eventually that hail is so large that ball of ice is just going to fall out of the air. But there are certain things that we need in order for these thunderstorms to develop. We need warm, humid air, and we need that air to be unstable. So there's a reason why most of our thunderstorms here happen in the afternoon. And that's because in the afternoon, our surfaces are the hottest. They've been collecting sunlight since the sun rose that morning. And generally like 2, 3 p.m. is when surfaces are going to be the hottest. So all of these things are why Florida has so many thunderstorms. We're getting that warm, humid air coming off the Atlantic Ocean. But we also have a lot of surfaces covered in things like asphalt. It's going to get really, really hot. When we have a hot ground and then cooler air above it, again, they're going to start interacting. It's going to lead that air into being unstable. So when we're looking at our thunderstorms, again, we need warm, humid air in order to develop them. But just like we see with hailstorms, we need those updrafts and downdrafts, the upward and downward movement of air within these cumulonimbus clouds. But eventually, with enough updraft, this cloud is going to get tall enough that precipitation is going to start happening. And it's not just going to be a small little drizzle. It's going to pour the rain. It's going to be very heavy precipitation. But we're also likely to get some strong winds, lightning, and if it's bad enough, eventually we're going to get hail. But you've probably experienced being outside in a storm. When it's raining, it starts cooling down the surface. And one of the things that we needed in order to form a thunderstorm is a hot surface. So as this rain starts cooling down the surface, it's basically going to kill itself out. This cold rain is going to cool off the surface, and eventually this thunderstorm is just going to start getting less and less intense until eventually the precipitation just stops completely. So a tornado is another thunderstorm, but this one's generally a lot more severe than a thunderstorm is, or at least it's going to do a lot more damage. But tornadoes are going to happen in a really short duration. Generally, we're talking about just a few minutes of a tornado actually being on the ground. But tornadoes are something that it's very obvious to see in a picture. And that's because we have this thing called a vortex. It's basically a column of air that is very quickly rotating as it's moving across the ground. But just like a thunderstorm, tornadoes form from these cumulonimbus clouds. We need those clouds of vertical development in order to form this really quickly rotating vortex of a tornado. But in the middle of this vortex, we're going to have really low air pressure. That means that all of the air pressure is trying to squeeze inside of the tornado, which kind of gives it this kind of suction power. But the most devastating part of a tornado is the wind, because we can see that tornadoes can reach up to 300 miles per hour. If they come in contact with a building, there is no way that that building is going to be able to remain standing. And if our tornado is large enough, we can actually see these smaller tornadoes that'll form off the side. So with our tornadoes, thankfully, there are nowhere near as many tornadoes as there are thunderstorms every year. We're going to see that on average, there are about 100 every year in the United States, but they're always going to happen with really severe thunderstorms. And just like we have a hurricane season here in Florida, places in the US that have frequent tornadoes also have a tornado season that runs from April through June. Again, when the surface is going to get a little bit hotter, allowing those thunderstorms to start to develop. So when we're looking at how and where these tornadoes form, they almost always happen along a cold front. Remember, that's the front where we're going to get extreme weather. So with these tornadoes, they don't just develop from any old thunderstorm. It has to be a massive thunderstorm that's called a supercell. It's just going to be a lot bigger and a lot stronger than the average thunderstorm actually is. But again, here, the reason why these devastating storms happen is because we have this really cold, dry air meeting with a warm, humid air. So we basically have both ends of the spectrum for our air, that continental polar and maritime tropical coming together. And because there's so drastic differences between the cold, dry, and then the warm, humid air, it's going to have a great contrast, and it's going to lead to a very intense storm. So for me, I actually went through an EF5 tornado back when I was in college. So tornadoes are something that are incredibly surreal and hard to explain. But within just a matter of minutes, my college town was basically destroyed. You would see, just like this picture, everything was just completely decimated. There weren't buildings after these kind of massive storms. So with a hurricane, we can shelter in place, but there really isn't a safe place to shelter during a tornado. So we're going to see that tornadoes happen, again, most often during our spring and early summer when that ground is starting to heat up. But we're also going to see that they happen in very specific locations. We're going to see what's called Tornado Alley in the middle of the United States. Here we have that continental polar air coming down from above, that cold, dry air, and maritime tropical, that warm, humid air coming from the south. And it's going to cause these basically polar opposite types of air to interact. So we're just going to have a strip down the middle of the United States where these tornadoes are most likely to form. But even though we don't live in Tornado Alley, here in Central Florida, we still have a decent number of tornadoes every year. And last fall, there was actually one here in Lakeland. But tornadoes are really difficult to forecast. So with a hurricane, we know weeks ahead of time that we're probably going to be experiencing severe weather. But with tornadoes, we might have a few hours to just a few minutes kind of warning to let us know that severe weather is in our area. So with tornadoes, it can be a little confusing because we have tornado watches and tornado warnings, and they're on two different levels from one another. So the tornado watch is the lesser of the two. It's basically saying, watch out, there's a possibility that a tornado might form today. So these are the most common types of warning. They just want to make sure that people are aware that we have the conditions that are perfect for a tornado to form. But the tornado warning is the more severe one of these. This is the one that you really absolutely have to listen to and find shelter. The tornado warning is actually warning you that there is a tornado. It's either been seen by a person or it's been picked up on like a radar from the weather. So with a tornado warning, it's not just saying, hey, one could develop. The tornado warning is warning you that there is a tornado nearby. So decades ago, generally these tornado warnings were only issued when someone saw a tornado and called it in. But now we've increased Doppler radar to the point that we can very quickly pick up where these tornadoes are and alert the people a few minutes sooner so they can find shelter. So again, our tornado watch is basically saying, watch out, a tornado could develop. But our tornado warning is warning you that there is a tornado. So now we're just going to move into hurricanes, which is probably something we're all fairly familiar with. So these are the most violent type of storms on our planet. And it's because they happen over multiple days, so they can do a lot of damage. And these are gigantic storms. If I'm talking about a huge tornado, it might be a mile wide, but hurricanes are hundreds of miles wide. They're always going to form over areas of really low pressure. It's going to form in those cyclone areas. So with our tornadoes as well, if we need something to rotate, to spin like a tornado or a hurricane does, that low pressure in the center is absolutely essential. But our hurricanes always start off by forming in these really warm ocean waters. And that's because it has a convective activity. We're going to see that the differences in temperature and humidity is going to cause this air to cycle. It's going to help it start rotating or spinning, giving it that cyclonic circulation that we see whenever we're watching it move through. So there are a lot of storms out there that act exactly like hurricanes. But hurricanes, we need to have wind that's over 74 miles per hour. And it also has to have that cyclonic circulation. Basically, it has to rotate at a really fast speed of 75 plus miles per hour. But they're going to form in very specific locations, generally between 5 and 20 degrees north of the equator. This is because during our summer months, this is the area that's receiving the most sunlight on the planet. So the water in these oceans are going to get really, really warm from that extra sunlight. So with hurricanes, they're dangerous, one, because of the winds. We're going to see that the winds can reach almost 200 miles per hour. So there are going to be a lot of things just flying around. But the greatest issue, what causes the most damage with hurricanes, is not actually the wind. Instead, it's going to be storm surge. It's going to start creating these giant waves in the oceans. And it can lead to kind of like these tsunami kind of conditions. We're having these gigantic waves hitting near our shores, and it can cause significant flooding. But depending on where we are on the planet, we're just going to call these hurricanes different things. Here in the US, we call them a hurricane. But if we lived in the Western Pacific, here we would be like off the coast of Asia. We would call them a typhoon. If we lived in Australia, we would call them a cyclone. They're all the same type of storms. Just depending on where we are, we're going to call them different names. And we're going to see that the North Pacific actually has the greatest number of hurricanes every year. We might assume that it's Florida, but it's actually Asia that just gets a lot of these hurricane activities every year. So as these hurricanes spin around, as they rotate, an eye is going to develop. And the eye is going to be in the middle of the storm. So within this eye, there's basically not going to be any wind. There's not going to be any rain. It's going to be very calm weather. So if you go outside in the eye of the storm, it's going to be like there's not even a hurricane going on. So the eye is the very calm part of the storm. But surrounding the eye is going to be what's called an eye wall. This is basically going to be an entire wall of clouds that are spinning the quickest. So the eye wall is going to be the most intense part of the storm. So with this eye wall, again, it's very near the center. It's not the exact center, but it's going to be close to the center of this hurricane. And it's just going to be a giant wall of these cumulonimbus clouds, those clouds of vertical development that are spinning at a very fast speed. But because this is a low pressure center, we're going to see that as it's spinning around, the air is going to be rotating and rising upwards. So the eye wall, basically the boundary on the outside of this eye, is going to be the most intense part of our storm. This is where we're going to see the heaviest rainfall and the strongest winds. Once the eye wall passes us, we're going to have a few minutes of just pure calm as the eye moves over us. The eye is at the very center of the hurricane, and generally it's about 12 miles in diameter. So when the eye is passing over us, all rain and all of the wind is just going to stop. It's going to be like it's just a very nice day outside. And that's because as the eye is moving over us, it's not actually rotating. The eye wall is. So we're going to have the air coming down or descending through our eye and moving from higher altitudes back down towards the surface. As it's going towards the surface, this air is heating up. So this is going to be the warmest part of the entire storm. So we see that hurricanes develop in very specific parts of our planet. And that's because they need those really warm ocean waters to develop. And most of the time, we're going to get our hurricanes in the late summer. Again, the time of the year when these oceans are just getting more sunlight than the rest of the year. They're just going to get a little bit hotter. So basically, anywhere with these nice warm tropical waters is going to start developing hurricanes, except for two locations, in the South Pacific and the South Atlantic. So if we were to live in the Southern Hemisphere, we would have less issues dealing with these hurricanes. But we see a lot of hurricanes in our northern hemisphere. But we're also going to see storms that are going to develop that aren't 75 miles per hour. These are still strong winds, though. So these are just other types of tropical storms. They're basically just small hurricanes. So if our wind is between 38 and 74 miles per hour, it's a tropical storm. But if that tropical storm were to get any stronger, if it were to exceed 74 miles per hour, it would just turn into a hurricane. But we also have tropical depressions. Here, there's going to be a lot less damage because our wind is going to be less than 38 miles per hour. So if we could rank these based on wind speed, we would have a tropical depression having the lowest wind, then a tropical storm, and hurricanes having the most intense wind. So we're going to see that hurricanes, as soon as they start moving over land, they're going to start losing their intensity. So as they move from that warm ocean water, either on top of the land, where they're no longer getting energy from warm water, because now they're just on top of solid rock, we're going to see that that hurricane is going to start to die out. Or if that hurricane just keeps moving farther and farther north into colder waters. We also have a third way where basically air masses moving high in our atmosphere can cut off the hurricane. But generally, this one isn't very common. We see that most of our hurricanes start to lose their intensity, either as they move into colder water or they make landfall and they start moving over the land. So they lose their energy when they're no longer in contact with these warm waters. But as we know, hurricanes are incredibly destructive. But there are a lot of things that are going to affect how much damage a hurricane can actually cause. Obviously, we're going to see the strength of the storm being one of the most important things. Obviously, if we have a hurricane moving through at 180 miles per hour, it's going to do a lot more damage than a hurricane with 75 mile per hour winds. But it's also important to look at what kind of area is it making landfall? How big is the city and how dense is its population? How many people are living there? It's also important how we construct buildings. So we talked about it with earthquakes, but there are different ways that we can construct things that will make them more likely to survive natural disasters. So if we look at this image here, we'll see that the only remaining structure is this house. That's because it was built in a way that it was meant to withstand these hurricane strength winds. But building a house like this is very costly. It takes a lot of money to have walls that can withstand 185 mile per hour winds or windows that can withstand that. But we also want to look at how the ocean floor looks right along the beach, because it's going to play a big part whether the ocean floor here is a gentle or a steep slope. If it's a gentle slope, that hurricane is going to very easily move onto the shore. But if it's a very steep slope, like a cliff face, it's going to cause that hurricane to stall out over the water. It's going to start losing some of its intensity before it actually makes landfall. But just like with just like with earthquakes, we want to be able to put our hurricanes on a scale. We want to be able to talk about how intense one storm was compared to another. So in the case of hurricanes, we use the Saffir-Simpson scale. It's just going to tell us basically how strong was the wind coming from that hurricane. And we know that it can be anywhere from a category 1 up to a category 5 hurricane. And as you increase the number, you're just seeing stronger and stronger storms. But when we're looking at the destruction that comes during the hurricane, what does the most damage is storm surge. So here, this is where those giant waves along the coast are going to come into play. As the hurricane starts making landfall, it's going to pull massive amounts of water from the ocean inland with it. So it's going to cause some massive flooding, bringing all of this seawater onto our land. So storm surge is actually what causes the most damage in our hurricanes. But other things that are going to cause a lot of damage is just the wind. We're talking about entire days of very strong winds. Some of our weaker structures are going to be damaged or maybe just completely destroyed from these really high strength winds. But we can also see that if it takes days for our hurricane to move through, we can also see massive amounts of flooding that will happen. And we saw this a couple years ago in Houston. I think it was Hurricane Harvey. It just stalled on Houston. It took days for it to move out of that city, and it rained so much that the entire city flooded. So with our hurricanes, scientists get a lot of beef about why they can't predict hurricanes so well. And they're trying to predict weather. We know that that's not really easy to do. There are a lot of different factors that are going to affect our day-to-day weather. So when you're trying to predict something a week in advance, generally there's a lot of uncertainty associated with it. So if you were to look at a map of a hurricane where it's just starting to form, you're going to see what's called a cone of uncertainty. Basically a cone shape surrounding where the hurricane is starting and telling you where it might be. You'll notice that this cone of uncertainty, the more we go into the future, the wider that cone is going to be. Not just because the more we're trying to predict in the future, the more uncertainty there is with that prediction. If we're just talking about a day of movement, we can be fairly sure at least which direction that hurricane might be moving towards. But if we're trying to predict a week in the future, there's a lot of uncertainty. So that cone is going to get a lot bigger. So that's it with our weather chapter. Again, I'm not going to be covering chapter 15. Take a few extra minutes, do some self-care, play a video game, find something to help relax you right now. I think we all need a little bit of that. So this will be the last chapter that we're covering. There aren't going to be any quizzes on chapter 15. The PowerPoints are up, but I'm not going to ask you about them on the quiz or on the exam. So are there any questions about this last virtual class?